So the next topic that we will cover is complex conjugates. So in order to understand what that is, let's take complex number z equal to x plus iy, and then the complex conjugate is denoted by z bar, so we read this as z bar, and it's given by x minus iy. So the only thing that you do here is you switch the sign of the imaginary part. And so a couple of properties that follow from that definition. So if we take the real part of the complex conjugate, we get x again, so that's the real part of the original number. If we take the imaginary part, that's minus y, so that's minus the imaginary part of the original number. If we take the modulus of the complex conjugate, we get that's x squared plus minus y squared. So that's the modulus of z, so the modulus doesn't change. And then last, if you take the argument of the complex conjugate, what you end up with is minus the argument of the original complex number. So the last one you may have to think about a bit, but basically you look at the tangent and or the arctangent and then go from there. And what that means is that the complex conjugate has a very nice interpretation if you look at the complex plane. So if this is our complex plane and this is our z equal to x plus iy, then z bar has coordinates x, so the x value stays the same, but the imaginary part now is minus y. So if this is y here, then our conjugate has coordinate minus y, and we end up with this point right here for complex conjugate. And so the complex conjugate is basically what you get if you reflect the number z across the y-axis. So these 2 points are each other's reflection across the x-axis or across the real axis. And a few more properties that are useful to keep in mind. We have that a number is equal to its complex conjugate if and only if the imaginary part is equal to 0, and that's the case if and only if the number was a real number to begin with. And secondly, a number is equal to minus its complex conjugate, minus z bar, if and only if the real part is equal to 0, and that's the case if and only if z is purely imaginary. So with that, let's now talk a little bit about doing arithmetic with complex numbers. So this is summing, dividing, multiplying, and so on. So there's an algebraic rule that we can elucidate, and then a geometric one. So let's assume that we have two numbers, z equal to x plus iy and w equal to a plus ib. And we want to add those two together, z plus w. What do? Well, we just calculate with I as if it was a real number. So we take x plus iy plus a plus ib. and we move the real parts until they're together, x plus a, and now we factor out the I. We have iy and ib here, so that's I times y plus b. So we get a new complex number where the real part is just the sum of the real parts of the original number, the sum of the real parts, and the imaginary part is just the sum of the imaginary numbers. There's also a very useful geometrical representation, and it goes by the name of the parallelogram rule. So let me show you how that works. So what we do here is we take our two complex numbers. So let's call this one Z and this one W. And then we draw the parallelogram that's spanned by these two edges. And then Z plus W is basically the diagonal of this parallelogram. So this is Z plus W, or which is also equal to W plus Z. And so this is often useful if you want to reason about where the sum lies in the complex plane. And there's an addition for what it means to subtract two complex numbers. So what we'll see in a minute is if you take a complex number and you multiply it by -1, what that does is it reflects the complex number through the origin. So the purple bar here is -W. And now if you want to subtract W from Z, that's the same as adding -W and Z. So we use our parallelogram rule again. We draw this parallelogram like this, and then we take the diagonal, and this gives us Z minus W. So this is often useful again if you want to reason about where they lie in the complex plane. Then just one thing that is easy to check. If we take the sum of two complex numbers and we take the complex conjugate of that, that is the same thing as taking the complex conjugate first and then summing the two numbers together. So the proof is very easy. If you take the complex conjugate of the sum, we use the expression that we have here, that's x plus a minus I y plus b, and we can write it as x minus iy plus a minus yb, and we see that this is z bar and this is w bar. So this is also a useful property to keep in mind. So for the product of two complex numbers, you can do pretty much the same thing. So just calculate, but keep in mind that I squared is -1, and use that whenever you have to. So let's say we have z equal to x plus iy and w equal to a plus ib. Then what do we have for z times w? Well, it's x plus iy, a plus ib. And now we work that out to get xa plus I squared yb, and then a bunch of terms in I, so I times ya plus xb. And the only thing here to remember is that I squared is -1, so we can write that also as xa minus yb plus I times ya plus xb. I don't remember this rule, I just calculate, and if necessary I write out what everything is in coordinates. So there's a useful special case that you should keep in mind because it will make a lot of calculations easier. If you take a complex number times its conjugate, you get x plus y times x minus y, iy, and if you work it out, you get x squared minus I squared y squared plus I times xy minus yx. And now you see, well, I squared is minus 1, xy minus yx is 0, and this simplifies to x squared plus y squared. So what we have here is the modulus of z squared. So the rule here says that z times z bar is equal to modulus of z squared. There's a couple of properties, furthermore, that are also useful to keep in mind. So the first three are standard ones. So we have commutativity, meaning that z times w is equal to w times z. So you can switch the order of multiplication. We have associativity, meaning that if we multiply three complex numbers together, we can choose to do the multiplication in any way we want. So we can either multiply first z1 and z2 and then z3, or we can first do z2 and z3 and then z1. The result will be the same. We have distributivity, so z1 times z2 plus z3 is equal to z1 times z2 plus z1 times z3. And then last, useful property for the conjugate, we have that if we take the conjugate of a product, that's the same thing as taking the product of the conjugates. And this is also often useful in calculations. Now, when we come back to our polar form, there's a particularly nice form for the product of two complex numbers. So let's take w equal to, in polar form, r times cosine theta plus I times sine theta, and z equal to s times cosine phi plus I times sine phi. So in particular, what do we know? Well, the modulus of w is r, the argument of w is theta, the modulus of z is s, and the argument of z is phi. And now let's multiply these two together, so we get w times z is r times s, and then cosine theta plus I sine theta, cosine phi I sine phi. Let's work that out. We get cosine theta cosine phi, and then minus sine theta sine phi. That minus comes from I squared, and then the terms in I, we get I times cosine theta sine phi plus sine theta cosine phi. And that should ring a bell if you look at those expressions for a bit, because what you have here for the real part is that this is just cosine of theta plus phi. And for the imaginary part, what you end up getting is that this is sine theta plus phi. So in conclusion, we can write the product as r times s cosine theta plus phi plus I times sine theta plus phi. And what that tells us is that if we take if we take the modulus of the product, so the modulus is basically the thing that you get up front here. So that is my R times S, and I get that this is equal to the modulus. So R, that was the modulus of W, and S, or that's the modulus of Z. And what we get here, so let me just write it on the slide here. So this was the modulus of the complex number. If we look at what we have inside the cosine and the sine, that's the argument of W plus Z. And so we get that the argument of W plus Z is theta plus phi. And if we look back at what theta and phi are, well, that's the argument of W plus the argument of Z. So multiplying complex numbers in polar form is very easy. You just multiply the moduli and you add the arguments together. And now there's a more general expression for this. If we multiply n things together, so more than 2, so if we take the modulus of Z1 times Z2 times ... Zn, that is the same thing as taking the product of the moduli, so Z1 times Z2 times ... Zn, and the argument of Z1 times Z2 times ... Zn, that is equal to the argument of Z1 plus the argument of Z2 plus ... plus the argument of Zn. And from that we have a nice little theorem called the theorem of de Moivre. So that's another French mathematician. So let's take Z equal to cosine theta plus I times sine theta. So in particular, what that means is that the modulus of Z is equal to 1. And now let's take Z to the power n. So that's Z times Z times ... Z. So n times. And the first rule gives us that the modulus of Z to the power n is the modulus of Z times the modulus of Z times the modulus of Z. So that's 1 times all ones. And that gives us 1 for the modulus. And the argument of Z to the n, that's arg Z plus arg Z plus arg Z n times. So that's n times the argument of Z. That's n times theta. And so from that we have that if we represent Z to the power n in polar form, what is it? Well, it's the modulus 1 times cosine of the argument. That's n times theta. We just derived that, plus I times sine of n times theta. And we can write that a bit different to say cosine theta plus I sine theta. So now I'm writing out what Z is. To the power n is equal to cosine n times theta plus I times sine of n theta. And this deserves its own box because that's the result of the theorem. So this makes raising a complex number to a power very easy what you basically have to do is just multiply the argument by that power. So the power becomes this multiplication here inside. And then now that we know how to multiply, we can also divide. And here, if we take z again equal to x, y, and w, a plus ib, then what we end up with is that this is a number of the form a plus ib in the denominator. And here you might wonder a bit, okay, how to make sense of this number. And the answer is, well, you can make sense of it by multiplying by the complex conjugate of the denominator. So what we get is z over w is this, and so now we multiply by the conjugate of the denominator. So the conjugate is a minus ib, and we have to put that in the denominator as well. And now if we multiply out what the numerator and the denominator are, we get x times a, and then plus y times b, plus I times ya minus xb, divided by, and here we have complex number times conjugate, that's the modulus squared, so that's a squared plus b squared. And so now the denominator is a real number, so we can also write it as xa plus yb divided by a squared plus b squared plus I times ya minus xb a squared plus b squared. So in particular, what you have here is that these two things, this is a real number and this is the imaginary part. So they're both real numbers, but this is the real part and this is the imaginary part. As with the rule for multiplication, I do not memorize this explicitly, I just calculate whenever I have to. Some useful properties. So first of all, if we take the modulus of z divided by w, that's the same thing as dividing the modulus of z by the modulus of w. And secondly, for the argument z times w, you can take the argument of z minus the argument of w. And sometimes you have to be a bit careful to make sure that it ends up in minus pi plus pi. So I just want to add one thing here, so don't memorize this rule. Just calculate. The only thing that you have to know is I squared is minus 1, and square roots are a bit weird, but we'll talk about that later. Some useful properties for calculations are the following. We've already seen a couple of those. So if you take the complex conjugate of a sum, that's the same thing as the sum of the complex conjugates. Same thing for a product. If you take the complex conjugate twice, then you get back the original number. So you can easily see that if you write it out. So complex conjugate just flips the sign of the imaginary part. So if you do that once, you get 1 minus sign, and if you flip it again, that goes back to plus. So doing complex conjugate twice is the same thing as doing not at all. And then slightly academic but useful property, if you multiply two complex numbers together and you get 0, that means that either z was equal to 0 or w was equal to 0. So it's the same property as for real numbers, but just for complex numbers. And then a useful meta property. So if you want to take the conjugate of an expression, so not just of a single complex number, then what you can do is take the conjugate of every term. So in particular, don't write out what the expression is, just conjugate each term and then see what you get. So for instance, let's say we have z equal to 5 plus 6i times 8 plus 9i squared divided by 3 plus 4i. So then you could work this out and figure out what complex number it really is. But to take the complex conjugate, just take the conjugate of each term. So in this case, it basically means replace I by minus I. And so we get for the conjugate that it's 5 minus 6i, 8 minus 9i squared divided by 3 minus 4i. So just one line calculation. So this also works if you have another complex number in the expression. So let's say you have little z is equal to I times capital Z minus 1 divided by capital Z plus 1. Then Z bar is, well, you replace I by minus I. And now Z, you have to take the complex conjugate of that, so you get Z bar minus 1 divided by big Z bar plus 1. So just a useful rule of thumb. And then last, to finish up, let's calculate a bit with some complex numbers. So for the first example, let's calculate Z equal to 3 plus 5i times 4 minus 2i. So don't use the rule here that we derived, just calculate. 3 times 4 plus 5 times minus 2 times I squared. So I'm just going to write it out all in full, and then later on we'll do it quicker. So plus I times, or 5 times I times 4 plus 3 times minus 2 times I. And if you clean that up, you get 12 I squared, that's minus 1. So 12 plus 10. And then I times 20 minus 6. In other words, you get 22 plus I times 14. And so the modulus of this number is square root of 22 squared plus 14 squared, and that's the square root of 680. The argument of z is the inverse tangent of y divided by x. So you can simplify that a little bit, but not a lot. 7 divided by 11. And here it's just the inverse tangent, because remember, that's the rule for if the x is bigger than 0. For the second example, let's have a look at z equal to 7 plus 3i divided by 4i. So we said, okay, to figure out what the division of complex numbers is, multiply by the conjugate. So let's do that. Minus 4i minus 4i. And then we work that out, and we get minus 28i, and then plus 12 for the numerator, and for the denominator, 4i times minus 4i, that's 16. And we can simplify that a little bit to become 3 over 4 minus 7 over 4i. So now that's a good calculation, but you can be a bit faster here. So an easier way to get to the same result is use the fact that we only have a imaginary number in the denominator, so we can do the division term by term. So it's 7 divided by 4i plus 3i divided by 4i. And so, of course, the i's cancel, and we get 3 over 4, that's this term, plus 7 over 4 times 1 over I. And what is 1 over I? Let's do that up top here. So 1 over I is multiplied by the conjugate minus I minus I. So it's minus I in the denominator, and then minus I squared in the, minus I in the denominator, minus I squared in the numerator, and we get that this is minus I over minus minus 1, so just minus I. So in other words, 1 over I is minus I, and we're left with 3 over 4 minus 7 over 4 times I, same result as before. An example where we can't just divide z equal to 1 plus I, 1 minus I, so we do the same thing as before. We multiply by the conjugate, 1 plus I, 1 plus I squared, and then here number times conjugate. We know what to do with that. It's the modulus squared, so it's 1 plus 1. And let's work out what we have in the numerator. 1 plus I squared is minus 1 plus 2 times I divided by 2. And if we simplify that, we get that this is just equal to I. In the last example, I to the power 2021. So in order to do this, let's write it as I times I to the power 2020 times I. And that's useful because now we can write the power as I squared to the power 1010 times I. So this is minus 1 to the power 1010 times I. So this is also just I, because this simplifies to plus 1. To keep in mind that is very insidious. Caveat or a warning is that if you have complex numbers, the square root of a times b is not equal to square root of a times square root of b. For a, b complex or even just negative real numbers. And you can see that quite easily on an example. So for instance, if we take minus 2 times minus 3, which is 6, so the square root of that is the square root of 6, but the square root of minus 2 times the square root of minus 3, that is equal to square root of 2 times I times square root of 3 times I, and that's square root of 2 times square root of 3I squared. So that's minus square root of 6. So these two things are not the same. So sometimes this pops up and you have to be very careful. This is one of the areas where complex numbers behave just a little bit different than